Alright guys, the limit as x approaches 0 of 1 over x squared. Start with the method of choice, direct substitution. Notice that that is going to give you undefined. So again, we need to use our common sense and we need to analyze the graph near 0, near x, as x approaches 0. Alright, go ahead and draw your graph. This, identify 0, and let's go ahead and see how the function behave as you pick a number near 0 from the left. So let's say if you pick this value, which is a really small number, right? That's really near 0, but it's approaching 0 from the left. What are you going to get? Well, you're going to get, so when x is approaching 0 from the left, what are you going to get? You're going to get 1 over that number squared, because that's what the function tells us to do. The function tells us to square. What does that do? Well, it makes this number a positive number. Alright, it makes that number a positive number. What does that mean? Well, it means that 1 divided by a really small number is going to be positive infinity, because now you have two positive numbers. How does the graph behave? Graph's going to look like this. Okay. Similarly, when you pick a number near 0 from the right side, let's pick the same number, and hopefully you know what happens here. So when x approaches 0 from the right, you're going to get 1 over that number square, which is going to be 1 over a really small number, right? Now, since they're both positive, it's once again going to be infinity. So, guess what, guys? The definition of a limit holds in this case. Since the limit as x approaches 0 from the left equals to the limit as x approaches 0 from the right, we say that the limit equals to infinity because those are the same. Okay, so a little bit of different situations. Again, if you want a bit more clarity, make sure you check out that Khan Academy. That's going to help you out a lot. Okay. Good. As we're finishing up the last page here, I want to introduce you to two special limits. And at this point, I just want you to remember them. And then later on, we're going to prove why they work out. The limit as x approaches 0 of sine of x over x equals to 1. Keep that in mind. Here's a graph to prove that for you. You can graph this using your calculator. And you'll see that as the function gets near 0, the function has a height of 1. Okay? So you can actually prove it by graphically. But we're going to work more with it later. Awesome. Here is another one that I want you to remember. Similar to the first situation, sine of 5x, the limit as x approaches 0 of sine of 5x over 5x, what do you think it is? It is equal to also 1. Alright? It is also equal to 1. Okay, so keep that in mind. These are the two things I want you to remember. If that number was a 6 and that number was also a 6, then that limit is still equal to 1. If that number is a 3 and that number is a 3, then the limit also equals to 1. Awesome. Good. So remember those two. Alright, now we're going to use this special limit to evaluate other limits involving similar circumstances. So say if we're trying to evaluate the limit of sine of 5x over x, right? The trick is to get a 5 down here. That's the trick, so that we can use this special limit. Alright, so how do we accomplish that? Well, what we're going to do is we are going to write this limit as this. So the limit, I'm going to write this as, I'm going to take 5 divided by 5, that's 1, times the original problem. Okay, and by doing that, I did not change the original problem because I'm multiplying the original problem by 1. So what? Well, guess what? We have accomplished what we wanted. We wanted a 5 in the denominator, so we got it. We got a 5 down here. See? Like that. All right. Well, how does this constant 5 affect this limit? Well, the limit of a constant doesn't do anything. So what we do now is we kind of just pull the 5 in the front, pull this 5 in the front, and then you have your limit problem looking like this. Okay. And from the previous problem, we know that that equals to 1, right? Right here, see? And then you bring the 5 down. 5 times 1 is 5. Awesome. So, hopefully from example 6, 7, and 8, we can maybe generalize what are the values or the answers to these limit problem. Okay. I want you to note that the answer to this problem is the same as this number. Interesting. Okay, so in general, whenever you take the limit of sine of b of x over b of x, as x goes to 0, you get 1. Alright? However, if you take the limit of sine of b of x over x, as x approaches 0, you get b, which is kind of like that problem. Okay? Awesome. So keep that in mind. Remember these. Here's our last problem for you. A ball is dropped from a height of 144 feet, and its height after follows the model of this function. The velocity, which means how fast the ball is moving at a specific time, is defined by this limit. Alright? If that's A, that's A, and that's A. So we're just gonna change these numbers. Let's say if I want to find, hey, how fast is the ball moving after 2 seconds? I will replace that by 2, that by 2, and that by 2. Alright, so here's our first question. Again, before we start, this is how we find speed, or I'm sorry, velocity. So, how fast is the ball falling at 1 second? What I have to do to find the speed at 1 second is to replace the letter A with the number 1. So, limit as t approaches 1, s of 1 minus s of t over 1 minus t. Right? We know what s of 1 is because you can figure out what s of 1 is. Okay? And if you plug 1 in there, what you're going to get is you're going to get 128. So 128. Okay, minus s of t over 1 minus t. Alright? Now, to evaluate this limit, we can try direct substitution. If you do try direct substitution, you're going to get 128 minus 128 over 1 minus 1, which means that you're going to get indeterminate form. Alright? Unfortunately, the factor technique that we accomplished earlier and the rationalization technique isn't going to apply to this problem. The only way for us to find the answer is to go back to the old traditional method and use either a table or a graph. Alright, a table works well with this problem, but I'm going to use kind of like a modified table. What do I mean by that? Well, a table means that I'm listing all the values of t that's approaching 1. So what I have to do is I have to see how the function behaves when I plug a number that's really close to 1. So as I'm approaching 1, so let t equals to 0.9999. That's actually really close to 1. I want to see how the function behave, right? So what do? I would take that and I replace it in there for that t and for that t. Okay, so I'm going to get 128 minus s of 0.9999 over 1 minus 0.9999. Alright, I have typed the function s of t into my calculator, and I'm going to go ahead and plug 0.9999 in and see what the value is. So type that into your calculator, pause the video if you have to. So I'm going to type in those values, 0.9999, and I need to save this number into the calculator. That's through store X confirm. Okay, so I store that number into the calculator. I'm going to go ahead and plug it into the function by hitting the option bars, slide over to Y vars, hit enter 2 more times, 1, 2, and maybe you have to hit another time, okay? But you're going to get 128.003199.8. I want you to copy down everything. So 128 minus 128.003199.8, and then you're going to subtract the bottom, so 1 minus 0.9999. That leaves us with 4 zeros, 0.1, 2, 3, 4. Take the difference and then divide. So I'm going to take 128 minus 128.003199.8. Okay, divide that by 0.10001. Hey, guess what? It's 32. It's negative 32 feet per second. Okay. What do you get? You get negative 32 feet per second. And that's how fast the ball is going after 1 second. Or how fast the ball is falling after 1 second. Okay, good. At what time does it hit the ground? Well, this is a height function. It hits the ground when s equals to 0. So start with this. This function tells you how high it is above ground. So if it's going to hit the ground, then that equals to 0. So replace that with 0. Okay. And then try to solve for t. Divide both sides by 16. That leaves you with 9. And then you ask yourself, what number square give you 9? Or you can take the square root of both sides, like this. Okay, and the two answers are 3 and negative 3. But remember, time can't be a negative number, so you just say it's 3 seconds. That's when the ball is going to hit the ground after it is dropped. Okay, good guys, hang in there. This is the last question. What speed is it traveling when it hits the ground? Alright, so it hits the ground at 3 seconds. So the big question is, how fast is it traveling at 3 seconds? Going back to the definition on how we find velocity. So I want a to be equal to 3 because I want to find the speed at 3 seconds. Okay, so go up down here and say, alright, a equals to 3. Start with defining your limits. This is the formula for us to find speed. Okay. We know that s of 3 equals to 0 because we found that that's 0 when t equals to 3. So we know what it is. So we plug that in there and then leave this alone. Alright, so we have to kind of go back to our method. We want t to approach 3. So let's choose 2.9999 for t and plug it in there. Okay, so when t equals to 2.9999, what does this equal to? So I'm going to do it with a calculator and then we'll plug it in. So first, type 2.9999 See? And we're going to store that into the calculator. Confirm by putting enter, pushing enter. Evaluate the function, vars, y vars, hit enter 3 times. 1, 2, 3. 0.00959984. Copy everything down. So negative 0.00959984 over 3 minus 2.9999. Okay? So to make 4 zeros. Negative 0.1234. Okay, divide those two, and you get your speed. So 0.00959984 divided by 0.1234. That's 96, guys. So you get 96 feet per second. So on impact, when the ball hits the ground, it hits the ground at 96 feet per second. Okay? Awesome. I will see you guys in class.